Oh, here we are continuing our discussion with limits. So today we're going to be looking at how we can solve limits with asymptotic behavior. For example, what would happen if x either approaches infinity, or what would happen if we even approach a vertical asymptote? And we talked a lot about this in pre-cal, you might remember, and this is basically dealing with rational functions. So today we're going to really discuss about why rational functions behave the way they do. So let's first talk about vertical asymptotes. So a vertical asymptote, you're going to notice all of these are single-sided limits. That's going to be the big thing. Hopefully you notice right there that these are all single-sided limits right here. We'll talk about what happens if it's not single-sided in just a few moments. So when we look at the first example right here, we have the limit as x approaches 3 from the left right here. And what we want to kind of understand is if I were to plug in this 3 right here, we would get 1 over 0, which is a big no-no since we can't divide by 0. Now be careful, again, this is not indeterminate like we talked about yesterday or the day before. It's not indeterminate, so we can't solve it by our factor cancel method or one of those other techniques. So we have to think, oh, well, what's happening here? So we have two options here. Option 1, I could just sketch this. This is not a hard rational function. I can get the vertical asymptote. That's just 3. I can even know what the horizontal asymptote is. Since the degree on bottom is bigger, it's y equals 0. And I can even find a point. This is all you really need to do a rough sketch of any rational function. For the point, I'm going to use the y-intercept, which is easiest. So if x is 0, I get negative 1/3. And I can sketch this graph. At x equals 3, and my horizontal is y equals 0. At negative 1/3, not drawn the scale. Your pre-cal teacher wouldn't accept this, but they're not here right now. So if I graph this, remember, functions are attracted to asymptotes. So this graph is going to be below, and it's going to go down. On the other side, on the flip side, though, we look at multiplicity. There's none here, so it's going to flip. So if one side goes down, the other side has to go up. And there's our rational function. So now I ask, well, I'm approaching 3 from the left side. That's what that little minus sign there, recall? So we're approaching from the left side, and this is going down right here. So we say this is approaching negative infinity. In other words, what's happening is that this is decreasing without bounds. And we can solve this very easily just by graphing these, just from what you learned in pre-cal. For example, let's take a look at number 2. If I plug in the 4, if you notice, again, we get this 1 over 0 right there. We don't like that. So which means we're going to graph this one. And this one's not that hard to graph. My vertical asymptote, see, I'm going to have to write this down. My vertical asymptote is at 4. And again, my power on bottom is bigger, so it's going to be 0. And if I let my y-intercept, if I let x be 0, we get positive 1/16. Be careful of multiplicity here, right? Remember the point, ready, is just 0, 1 over 16. Sometimes people write that down, it helps. Because of the multiplicity here, if this side goes up, we already know that this side has to be on the same side of the x-axis, or of the horizontal asymptote. And we are approaching, this time from the right side, and of course if we approach from the right, this is approaching positive infinity, where we say this increases without bounds. Take a pause. See if you can just sketch number 3. I'm going to go ahead and do it, but pause right now if you need to. Alright, so for number 3, same idea. My x-intercept, if I try plugging that in, I get 1 over 0. We don't like that. So there's my vertical. Add sound effects. Makes it a little bit more exciting. My horizontal still 0. And if I cover the 0, I get a point 0 1/3, which is going to be above. So we know that this is going to go up like a disco duck. And the other side, because this side goes up, the other side has to go down like a disco clown. And there's our graph. And now I can answer. We're approaching from the left. We're approaching positive infinity. Or again, we are increasing without bounds. Very easy to do. All right, so for number 3, let's take a look here. Same idea. But this time I have my vertical, if I plug this in, I do get 1 over 0, which we don't like. So my vertical asymptote is at -3 this time. and that's 0. If I cover, I'm at the point 0, 2/3. Whoops, ran out too far. And so this is going to go up, and the other side has to go down, like a disco club. And we're approaching again from the right side, so this is approaching positive infinity. Now, let's have some fun. What if we said, what's the limit as x approaches -3, this time from the left of this function? Well, that time it's going to go down, so this is going to be, of course, negative infinity. Very good. But now let's up the ante here. What if we approach -3? Now remember, this is what we call the actual limit itself. Now these are limits, but they're more of the test to see if this limit actually exists. Now one's going from positive infinity, the other one's going to negative infinity. So of course, these aren't the same, so this is going to be a D and E. It does not exist. But the reason it's D and E is not because they're not the same. It's even worse than that. It's the fact that we have an asymptote here. Even if both sides go up, one side goes up and the other side goes up, like so. The answer here is the limit here is still D and E. And to understand this, let's take a look at the following Let's take a look at the following problem. Let's say we want to find the limit as x goes to infinity of 3x squared plus, 2x. Now, if I let x go to infinity here, this is infinity, this is also infinity. And if we were to kind of add them together, of course, that's infinity. Now, we never, ever write that. We really are thinking it. So that's going to be infinity. But what happens if I switch it around? As x goes to infinity, we get 3x squared, sorry, not switch around, but minus 2x. Now we get more of a problem. Because if I plug in, I'm going to get infinity minus infinity. And that is really weird, because some people think, oh, that's 0. We really don't know. This is actually kind of what we call indeterminate again right here. So that is bad. We don't like that. And the problem is, if as x goes to infinity, we know 3x squared also goes to infinity. If x goes to infinity, we also know that 2x goes to infinity. So that's our issue. They're both infinities. But remember, infinity is a thought. It's not really a number. It's just an idea. So we really don't like to mess too much with infinity. So we have to go back to looking at the 3x squared and the 2x, their relationship. As x gets really big, I have this 3x squared and I have this 2x. So I know that as x gets really large, 3x squared is always going to be bigger than 2x, as long as x is bigger than, as x gets really large, not close to 0. So in other words, what is that saying? Well, that is saying that this infinity is greater than this infinity. So we're kind of saying infinity is greater than infinity right here, which is kind of, what? Infinity is greater than infinity? Yeah, that can happen because we have two different infinities. They're growing at different rates. So we kind of say that infinity cannot equal infinity. So that comes back to our problem right here. When we come back here, well, because I know that this infinity is greater than this infinity, this becomes positive infinity if I were to subtract them. Likewise, what if I did 2x minus 3x squared? Same idea. They're both infinities, but remember, because the 3x squared is bigger, this is going to approach negative infinity that time. Very kind of cool. Now, another way we can kind of look at it is algebraically. We can factor out an x, and now we get 2 minus 3x. And I can multiply. Well, that just becomes infinity times, and if I plug in here, negative infinity. So infinity times infinity, of course, is infinity, and a positive times a negative is a negative. But we can also kind of just rationalize through it. And this is actually a really good skill to have up here. Algebraically, it's nice, but it's a really good skill to understand that infinities don't always have to equal each other. And that's where we get to our problem right here. Just because they're both approaching positive infinity doesn't mean they're approaching at the same rate, doesn't mean they're going to reach at the same time. So as a result, we say that there is no limits at infinity. That the infinity will not, that the limit should not exist there. Some teachers will accept that, some books will accept that, but I prefer the D and E. And so we say it does not exist because at x equals -3, there is a vertical asymptote. Or x equals -3 is asymptotic. That's a cool word right there. That's your big word of the day. Asymptotic. It's asymptotic. Right. Now there is kind of a shortcut we can do here, and it's not too bad to do. We can pick a value. This says I want to approach -4 from the right. So I can pick a number close to -4 on the right. Okay? I could pick -3. So if I plug that in, ready? I would get -1 over -3 plus 4 squared. Now what's going to happen is this is going to give me a -1 over 1. So let's talk about this real quickly. Let's mention a really quick rule right now. Hopefully you guys kind of noticed, anytime we divided by 0, what did we get? We got some form of infinity. So that's kind of the rule. The limit as x approaches 0 of 1 over x is going to be plus or minus infinity. It's always some sort of infinity right there. So if I were to plug the 4 in here, my answer is going to, my -4, I'm either going to get a positive infinity or a negative infinity. Well, by picking that number really close to the right, that helped me. By picking that -3 and plugging it in, it's telling me that this is less than 0. Therefore, we're going to pick the negative infinity. And that's going to be our answer right there. This takes a little bit of practice. Graphing is always the best. Now, when it comes to trig values, we always want to kind of graph them. So in order to do trigs, we always look at where we have domain restrictions. For example, let's take a look at tangent of x. Tangent of x occurs that can't, where sine of x can't be 0. So here x can't be pi over 2, all those pi over 2's. So if I go from like negative pi over 2 to pi over 2, there is my asymptotes. And hopefully remember what tangent looks like. It looks kind of like this, right? Now your pre-cal teacher wouldn't accept that, but again, they're not here, so we're cool. So that's our graph for tangent. Looking at cotangent of x, this is where cosine of x is 0. So x cannot be 0 of the pi's. So if we were to graph it, negative pi, 0, pi. Cotangent is kind of like tangent, but sometimes the functions go down. And again, your teacher would never accept that graph, but it's for us. And it helps us because if we look at this example here, we want to find out what happens to cotangent as x approaches pi from the left side. So here's the pi. On the left side, this is going down the graph, going down like a disco clown, so that's going to be negative infinity. Likewise, if we look at secant, again, secant is where cosine is 0. And so x cannot be 0, I still messed up. That is cosine, and that is sine. Excuse me for that. Cosine is where cosine is 0. That's our pi over 2's again. Boy, I know I'm going to get a lot of comments in the comment section there, but sorry about that. So when we look at secant, we'll look at the pi over 2's, negative pi over 2. Positive pi over 2. Graph your asymptote. And think, this is one of a cosine, this is the flip of cosine. So cosine kind of looks like this. So we can get our bumps and our lumps. My humps, my humps, my humps. And that's going to help me here. This should be cos pi over 2, not pi over 3. And we're approaching from the right side, pi over 2. Well, there's pi over 2. From the right side, this is going down, so it's going to be negative infinity. Right there. They don't take too long to graph. And again, like I said, your trig teacher is not going to like that, but they're not here. So we got cosecant, this is where sine is 0, and that x can't be 0, and the pi's again. So if we got it, 0, negative pi, what happens when we eat too much pi? Goes down, 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 right? And then cosecant is sine, so we know what sine looks like. Kind of looks like this. Oops, got a wrong color there. There's a sine curve, and you can draw my hump, my hump, my humps. All right, and there's our graph for cosecant. And you can answer any question about that. All right, so going to part 2, we're going to take a look at what happens when we have a horizontal asymptote, okay?